Hello again, class. Welcome back. Hope you all enjoyed that first video. I know it was a little lengthy, but I wanted to really go in depth on that very first one to let you know I'm here for you. I'm here to explain everything as much as possible and hopefully guide you through this in this distance learning. So continue to check out the videos. I'll continue to post where the examples start. I won't list every one. That way you can just start there and hop around if you'd like. This second section here, we're going to talk about angle relationships and also similar triangles. So now not just two rays to create an angle, but actually making it complete and drawing triangles and even looking at other types of angles that we can also run into along this road. So here we go. Hope you're ready. So this first part of the notes is going to be talking about the different types that we're going to start with. And again, these can be done without parallel lines, but they don't hold as special of versions of the angles. When we look at them this way, it works out a lot better. So we're going to deal with parallel lines. As you can see there in the drawing, we're looking at line M and N in blue. And then the third line that we draw through at any angle, doesn't have to be that one, but it then creates the angles. And by angles, you can see that there's actually 8 different angles by just drawing this one line we call a transversal through those parallel lines. Okay, so a few names that we're going to have here and then the rules, and I'll give you angle examples based off of those numbers just so that you can kind of put the visual together. So the first type that we're going to see are called vertical angles. Okay, and notice I grouped the first 4 and then the last one by itself. Hopefully you remember what vertical angles are. Somebody's vertical jump in basketball, football, it's measured a lot, is up and down. So when you think of vertical angles, we're talking, for example, angle 1 is right above angle 4. And if I was to take this angle with those two sides and the other two sides that it was cut at that vertex there, that point, then these two angles look and appear to be what? And hopefully you said equal or the same. The fancy math term that we use for the same measurement but not in the exact same place is congruent. And because it doesn't mean exactly the same like equal sign does, the equality symbol, then we're also going to make it a little bit different. And so the rule is that they are congruent or the same measurement. The cool thing is for every single one of these first 4, that is going to be the same. So when I'm talking about congruency, I'm meaning that their measurements are the exact same, but they may not be in the exact same place. Okay, it's not the exact same angle, which is why we named it angle 1 and angle 4. Or another pair would be like 2 and 3, 5 and 8, or 6 and 7. Okay, so those are what are called vertical angles, and because we know that they are parallel lines cut by a transversal, we know that all of those pairs are the exact same measurement, congruent. Alternate interior, 2 different words there talking about the 2 different types of lines, the parallel lines and the transversal. So interior, meaning inside of the parallel lines. So in here, talking about angles 3, 4, 5, and 6 are what are called interior angles. Exterior would be on the outside of those parallel lines. So angles 1 and 2, 7 and 8. By alternate, we mean alternating sides of our transversal. Okay, so when we talk about an alternate interior angle pair, we know that they are the same measurement, even though they're not the exact same thing, so we call it congruent. So can you give me an alternate interior pair that therefore would be what is called congruent? And hopefully you said interior. Remember, we're only looking at angles 3, 4, 5, and 6, and we need to alternate. And if you look at 3, which would be the next smallest number there, 6 would be on the alternate side of it, but still inside, interior of our parallel lines. And what do you notice about 3 and 6? What do they appear to be? The same. Good. So 3 and 6 would be a pair, as would 4 and 5. Now when we look at alternate exterior, we're still alternating the transversal line from one side to the other, but exterior meaning we're looking on the exterior or outside of the parallel lines. So in this case, we're looking at angle 1 and alternating over to angle 8. And if you notice, those obtuse angles appear to be the same. So angles 1 and 8 would be a pair, as would 2 and 7. And again, those are called acute angles because they're definitely less than 90. All right. So continuing on, the last type that we're going to talk about is corresponding. That is congruent. And then we'll get to the last type that is it's in its own special category. But corresponding, I like to remind students in class, we're talking about a correspondent in the news. That's usually somebody that's not in studio, but they're out actually at the site. Okay. And maybe like the place that I'm at in the background, I went this summer in Shoshone Falls, Idaho. If we went there and reported from what they call the Niagara of the West or mini Niagara, then you would be what is a correspondent to me. So I'm reporting on that waterfall and you're actually there reporting on the same waterfall. So we're still the same in that sense, we're just in different places. So a corresponding angle is when you were to take an angle, for example, like angle 2, and if you were to actually physically take this angle and just slide it down to a different place, like angle 6. So notice if I took this actual angle here, right here, and I just slid it down, that transversal we called it, notice it would be the exact same red line, which would be this part here, and then it would be the parallel line to that blue one, which virtually is the same, just in a different spot. So that's why we would call angles 2 and 6 corresponding, because they are in corresponding or similar places and therefore are congruent because they're virtually using the same exact sides to make up the angle. Okay, so again, for example, 1 and 5 would be another pair. 2 and 6 we said. Another would be 3 and 7 and 4 and 8. Okay, those would be all the corresponding pairs that are therefore congruent. All right. So the last type that we're going to look at is what is called a same side interior. So no longer are we having to alternate, but we are still on the interior. So still looking at angles 3, 4, 5, and 6, but this time we're on the same side of the transversal. So you guessed it, angles 3 and 5 and 4 and 6. And I'm going to use a different color to let you know that these are actually different. So to highlight this, we're talking angles 3 and 5, 4 and 6. And looking at 3 and 5, those pairs, well, what do you think? They're definitely not congruent. So what are they? What makes them different? Why are we looking at this by itself? Well, we do know that angles 3 and 6 are the same, don't we? Because they're alternate interior angles. So we know that those two are the same. And we also know that angles 5 and 6 are what are called supplementary. So since I know the measure of angle 5 plus the measure of angle 6 is equal to 180, and because we know that angles 3 and 6 are the same, then that means I can just simply substitute out angle 6 with its congruent counterpart, angle 3, and say that those also have to equal 180. And let's see if you remember from the first section that we dealt with, what do we call two angles that add up to 180? Hopefully you said it. They add up to 180. They are called supplementary. And so those are the ones that are a little bit different as far as the pairs go for parallel lines cut by a transversal. All the other ones we really enjoy because they are the same. congruent. Okay, those are the only ones, same side interior angles, that we have to be a little bit more careful with because they are actually supplementary and not congruent. And you should see that they're definitely not the same because one is going to be obtuse, the other acute. So they are definitely not the same. So it works out really nice. The proof is pretty easy. Hopefully you understood the whole switching of these two things to add up to 180 for that straight angle that we had over there. Okay, so that's parallel lines. Now let's talk about connecting an angle with the two endpoints to make a third. And whether it's a right triangle or any other type, we want to now explore all three angles and what their sum is. And so there's a couple different proofs out there. It's pretty cool. Hopefully you know that the angle measurements of a triangle add up to, well, here's a quick proof in case you did not know the answer, because I couldn't hear you very well. You're going to have to speak. I'm just kidding. Looking at a rectangle or a triangle, we know that they are made up by definition of 4 right angles. And 4 times 90 is equal to 360 degrees. Of course, we are talking about a triangle. And therefore, what we want to do is take this and just simply cut it in half. Now, I went diagonally like that. You could go the other way. But either way, you can see I now created 2 triangles. And since I cut that 360 in half, we know that the measurement is also equal to 180 degrees. Now there's a cool proof that's a little bit more hands-on. It's kind of like a math magic project for you. And I have the directions right down below with some diagrams. So do me a quick favor, grab a little blank piece of paper and create a triangle. It's usually easy to create a right triangle by using one of the corners of it, and then just making a cut across and then getting that triangle. Okay, go ahead and grab a quick piece of paper and cut out or fold and tear the triangle. Okay, now you've taken care of step 1. Once you've drawn that triangle and cut it out, now I want you to actually make little arcs inside of each one of the angles, and if better, label them 1, 2, and 3, kind of like I did, so that you can see all 3 angles of your triangle. Because what we're trying to do is actually add up those 3 angles to see what their sum is. So now I want you to carefully cut or rip out all 3 angles. And it'll look a little something like this. And once you've done that, take all 3 of those angles, angles 1, 2, and 3, and line them up edge to edge like that, so that you create one continuous arc of your angles 1, 2, and 3. And once you have that continuous arc like that, hopefully you can see that it actually creates a straight angle, and therefore the sum of those 3 angles has to equal 180 degrees. Pretty cool little proof. I'm sure a lot of you have not seen that before. Very simple, very easy, something nice to do with younger kids because they can see that, they can touch it, they can feel it. And hopefully for you guys, it's just kind of cool and gets you excited about math a little bit. All right. For those of you that don't really care, here we go. We're moving on. You can just fast forward, right? So the last few things we want to talk about with triangles then is both their interior and exterior. Interior meaning angles, and the exterior meaning their sides. So we will then classify each one of these based on the type of angles and then the type of sides that we are given. And so if all the angles inside are acute, we call it an acute triangle, meaning that all 3 angles are less than 90. Okay. If there's one angle inside that is a right angle, then we call it a right triangle. And there can only be one. Why can there not be 2? Well, what's 90 plus 90? That's 180. And therefore, there cannot be a third angle. Therefore, we don't have a triangle. Okay? And then the last thing, if we don't have a right triangle, we can have what is called an obtuse angle which remember is that bigger than 90 angle. And again, therefore we can only have one, so we call it an obtuse triangle. Okay, so again, that's how we classify triangles based off of their insides, their angles. What about their outsides? Well, we could have these tick marks, meaning that those are the same lengths. That's the quick, easy way to say it without actually telling you what they are. And we call that an equilateral. Lateral meaning side, equa meaning equal. So if all three sides are equal, we call it an equilateral triangle. Now, if only two of them are, it's called an isosceles. And if none of them are the same, we call it a scalene triangle. Okay, so just a little moniker there for both the insides and the outsides. We can combine these if we know enough. For example, we can have a scalene right triangle, okay, or an obtuse isosceles triangle, things of that nature. So by them telling us that, they are telling us how the insides and outsides behave. So last few things here. I mentioned before, what does it mean to be congruent? Congruent to us means that they have the same measurement, which is the key there, but they can be in a different place. Okay. And then something new, we're going to talk about what does it mean to be similar? Now, again, we're talking about triangles here now, not just angles. So if I was to say that two triangles are congruent, what do you think that would mean? Well, that they're the exact same angle measurements and side lengths, but they could be rotated, put in different places. But what does it mean to be similar? Being similar would mean something to the effect that they're very close to being the same. And so we'll get into that a little bit right below. Okay. So if you look at the next line down there, it says, if two triangles are congruent, then they must be similar. But if you were to do the converse, the other way around, if you have two similar triangles, they don't necessarily have to be congruent. So how can this be true? Well, let's talk about first what it means to be similar triangles, and then we'll get into that. So down below, I have an example of two triangles. And as you can tell, they are very similar looking, no pun intended, but they are definitely not the same, congruent. One is much larger than the other. But if you notice, angle A and D are the same. B and E are the same. And C and F are the same. So does the order matter that we say these things in? Yes, because when you tell me that angle triangle ABC is similar to triangle DEF, then you're telling me that A corresponds to D, and B to E, and C to F, just like the drawing shows. Okay? And so there are only two things that have to be true in order for triangles to be similar. Corresponding, meaning in the same type of place, they have to have the same measurement. So that is a given. The insides do have to be the same, as is in this example, right? All these angles are the same for corresponding similar spots. But what does not have to be true? The sides don't have to be the same. But there is some relationship there. And in this case, it says that they're proportional. Well, what's a proportion? Hopefully you remember, they're fractions that are equivalent. Okay, so I could say, for example, that 1/2 is equal to what over 8? And you'd be able to tell me that the unknown part is 4/8. So if I tell you that this is a length of 1, and this is a length of 2, and this is a length of x, and this is a length of 8, do you see the corresponding sides? I put 1/2. So I went this side to that side, which means I have to go this side to that side in order for it to be equivalent. Okay, so that's what it means to be similar, is that the angles do have to be the same, but the sides are actually proportionate to one another. Twice as big, 3 times as big, or 1/5 as big. Okay, so going back to that question real quick, if two triangles are congruent, meaning what's the same? Hopefully you said everything, insides and outsides, then they have to be similar, because not only are the angles the same, they're proportional. They're 1-to-1. They're the exact same. However, if they're similar triangles, they don't have to be congruent because they don't have to be the same size. The lengths of the sides don't have to be the same. So that's the difference between congruence of triangles and similarity of triangles. This time they're calling it MNP and QSR. And if these two are similar, then we know about their angles. Corresponding angles are congruent. But what did we say about the sides? Because this time, that's what they want us to know, are the unknown sides of triangle QSR. So they gave us one. We need to therefore find what QS is as well as SR. What are those measurements? Well, remember, in similar triangles, we know that their angles are the same, corresponding angles, but corresponding sides are a certain ratio. We call it a proportionate. Okay? They are proportionate to one another. So the cool thing is you can kind of take this however you want. If you wanted to do 8/12, that's fine. Then you'd have to do 10 over this QS. So I'm going to go ahead and label this as X and this one as Y, just so that we can label it a little bit better. And therefore, if you wanted to do the, like I said, 8/12, then you can do 10 over X, or you can do 8/10 as long as you do 12 over X. You just have to be consistent no matter what you do with these to set up your fraction equals another fraction. We call it proportion. So in this case, I'm going to go ahead and keep it simple. I'm going to do 8/10 and set that equal to 12 over X to start. And this ratio right here is really nice because not only can I find it, I can actually reduce and simplify if I wanted to. Now, one thing I want to make sure that you guys do not do, it happens all the time, is do not cancel the 12 and the 10, okay? Don't cancel across an equal sign ever. The equal sign separates the two equivalent sides, all right? So the one thing, if you wanted to do that you could, is the 8/10. Okay, so if you wanted to divide this by 2 and get 4 and this by 2 to get 5, that's fine. Now you have two options at this point, actually a few more, but I won't go into too much. You can either multiply across the equal sign at a diagonal. We call it the cross product, okay, because we're multiplying product across the equal sign as well as the numerator and the denominator. Or you can go ahead and multiply by the LCD, which the least common denominator of each of these would be 5x. So there's a couple different ways to do this. Most people will just not think and do it this way and say 4 times x is 4x. And then 5 times 12 is 60. And so your last step there would obviously be to divide, to undo the multiplying, to get that to be a 1x. And then 4 goes into that. If you wanted to, you could divide by 2 twice. But 4 goes into 6 once with 2 left over. Bring down the 0 and then 5. So we just found that length QS, which we called X to make it simple, is a length of 15. Doing something similar for SR, which we called Y, we can go ahead and set up that 8/10, which since I went here over here, I don't want this. I already found it. So instead of 8/10, I'm going to have to do 8 over what? And you can actually do 10 over, but I would use the things that you were given rather than the one that you just found here. So I would do 8/12 and set that equal to 12 over y. And again, go ahead and cancel. 8 and 12 each have a divisor of 4. So 4 goes in this twice, 4 goes in that 3 times, and then you can do your cross product. 2y equals 36. And then go ahead and take half of that so that you get what y or rs is, or sr, and that would be the length of 18. So 2 different ways to use similar triangles, both on the inside, the angles that correspond to one another have to be the same, and then the outsides, the side lengths that correspond to one another have to be proportionate.